activity today. We're doing activity 3 in what is the future of Earth's climate. So in activity 3, you're going to see it's similar to computer modeling that we did with the greenhouse effect. So I'm going to go through these with you. Feel free to log on to Hasbot and manipulate the computer models as well. As you know, when I test you on this information, you will be required to answer questions using the models. So let me move this little thing out of the way. All right, we start off with solar radiation. And this first computer model, I'm going to go ahead and I'm going to move this toggle to slow and press play. Okay, what is this showing? This is showing the sunlight is coming in. Those are the yellow arrows. Make sure you can see those yellow arrows, okay? I'll zoom in. That represents sunlight. And we can see that sunlight, let's just follow one here, sunlight can get converted into these red dots underground. The red dots are heat. And finally, the red dots can actually be emitted back into the atmosphere as purple arrows. Those purple arrows are infrared energy, okay? So infrared radiation moving out. And we know infrared radiation is heat. The last thing on here are the green dots. They're kind of a pentagonal shape. The green dots, those represent carbon dioxide in the atmosphere. So we can certainly click on the key here. The yellow arrows are solar radiation. The green are carbon dioxide and the red are heat. Okay. And we're looking at how those interact in the atmosphere. So a couple of things you should know. The yellow, the solar radiation can do one of two things. It can be absorbed by a surface, or it can be reflected by a surface. Okay. Now, what can happen to the red dots? That's heat. That can be re-emitted back into the atmosphere as infrared radiation. Now take a look at how these interact with the green particles, the carbon dioxide. So I'm going to increase the amount of carbon dioxide in the atmosphere by erupting the volcano. I'll click down here where it says erupt. Now, if you take a look, the solar radiation is not affected by the carbon dioxide. What I mean to say is visible light, solar radiation is not reflected or absorbed by greenhouse gases. But what is reflected or absorbed is the purple arrows, and that is the infrared. So just to summarize, sunlight comes in. If it's reflected from the surface, it will be reflected back out to space. If it's absorbed by the surface and becomes heat, that can be re-emitted, but that heat now it can be trapped by greenhouse gases such as carbon dioxide in the atmosphere. Okay, we're going to go to page 2. Taking a look at carbon dioxide in the atmosphere now, we're going to go ahead, I'm going to click slow again and press play. Now we have two graphs. The rule is when you find a graph, the first thing you should do is read the title of the graph and then take a look at the axes. So the top graph over here is temperature change. And we're seeing a line over here, temperature change. The x-axis shows the year. And so we started in 2024. It's current and we're moving forward. And the y-axis shows the temperature in degrees Celsius. And this is a departure from. So we started at 0 and we're seeing what it does compared to that baseline. The graph below is carbon dioxide concentration. That's CO2. Okay. So you can see that's steady right now. We're not doing anything to the amount of CO2. We're going to leave it where it is. To manipulate this model, you should add or remove carbon dioxide to see what effect that has on temperature. So I'm going to go ahead. We're seeing the temperature here. We'd like it to stabilize. I'm going to go ahead and speed this up. Speeding it up hopefully will speed up the years as well. We'll see. I'm going to go ahead and cause the volcano to erupt. Okay. And you can see below that the graph just went up. And I can cause it to erupt again and cause it to go up higher and higher. Now, what if I go up above 100? Well, this model is such that it will readjust the parameters of the graph. So you can go really high with this. I know some of you might want to play around with it and see how much carbon dioxide you can get in the atmosphere. And what we're looking at here is, according to this computer model, and remember when we do claim evidence reasoning in science class, the evidence, one thing we can use for evidence is the results of computer models. And certainly we can question how valid a computer model is, but for now, let's just say that they are accurate. And so we're taking a look here at what is the effect of increased carbon dioxide on temperature. And you should be able to see that by comparing the graphs. So as we increase the carbon dioxide, you should see that the temperature also increased. Now let's remove carbon dioxide. If you can see the button in the middle here to remove, I'm just going to start clicking that. And what we're doing is we're actually taking carbon dioxide out of the atmosphere. And I'll try to get all the way down to 0. And you can see the effect that that has on temperature. So what we say is that there's a direct relationship, possibly a correlation, between the amount of carbon dioxide in the atmosphere and the temperature of the atmosphere. As I increase carbon dioxide, temperature also increases. You can see that move. And as I decrease carbon dioxide in the atmosphere, temperature decreases. Okay. I'm going to go to the next one. Page 3. Now you'll notice if you do this, there are certain questions that you'll have to answer in order to move forward. Yeah, feel free to write your answers in those if you choose to do this activity on your own. How does solar radiation interact with Earth? Now this is a different model. We're going to call this one, if I remember right, the solar radiation model. Let's just leave that for now. Okay, if I start this model out, what we have here is the sun. These represent the ground, and I'm going to go ahead and press play. And let me pause it. Okay, we've got some weird things going on here. So what we have coming from the sun, this is showing a short wavelength particle. We're going to call this a photon. A particle from the sun is called a photon. It has short wavelengths. And then these are shown as longer wavelength. That's the infrared light. So the photons are hitting the ground. They're causing the ground to warm up. And then the ground re-emits the energy as infrared. Got it? So let's go slow motion. And let's display the heat in the molecules. And it's going to show that as color. So I'll press play again. And you can see as the photons hit the ground absorbs some of that. Some of the photons can be reflected, and some are absorbed. Now, I can select different models on the left here. This is the effect of the sun on the ground. Here's the effect of the sun on carbon dioxide. So we see that the particles, the photons from the sun, do not affect the carbon dioxide. I don't see any changes. The next model is the effect of infrared energy on carbon dioxide. Okay. So now infrared energy, you can see infrared energy can be absorbed by the carbon dioxide. That causes the carbon dioxide to warm up. And then if you look closely, you'll see that after it warms up, it will re-emit the energy as infrared energy. So visible light, shorter wavelength light from the sun, it doesn't directly heat up the carbon dioxide. So the carbon dioxide does not absorb it, and the carbon dioxide does not block it. But after it hits the ground, the ground will absorb some of it. That then becomes heat, and the heat is re-emitted as infrared energy, which now can be trapped and absorbed and re-emitted by carbon dioxide in the atmosphere. The last model here is the sun on the ground and carbon dioxide. So now we can see everything come together. Okay. sun is hitting the ground. As infrared leaves, the infrared can interact with some of the carbon dioxide in the air, and so on. This just brings it all together. Feel free to play around with that. You can see what happens to the temperature on the far right. Okay, I'm going to go to the next slide. We're back to the Earth systems and greenhouse gases model again, and this one just asks you what factors are represented by the purple arrows and what evidence do you have. So once again, the purple arrows, I'll slow it down. The purple arrows represent the infrared energy, and what evidence you would have from that would be that the purple arrows originate from the heat in the ground being re-emitted, and we know that energy released as heat, the electromagnetic spectrum form of energy, is infrared energy. The next page. Atmospheric carbon dioxide over time. We're going to take a look at this graph. This is called the Keeling curve, named after Charles Keeling. You can see his name here, hopefully. And the story goes in the middle 1900s, in 1958, Charles Keeling decided to study the level of carbon dioxide in the atmosphere. He did this on top of a mountain called Mauna Loa. Mauna Loa is on the big island of Hawaii, and Mauna Loa actually means flat mountain. You don't have to know that. Okay, and what he saw was every year there'd be a time when you can see this squiggly line here. That's 1 year. All right, as it goes down and up, that's 1 year, because there's a time during the year when we get an increase in carbon dioxide on Earth, and then time when that level decreases. So it increases that part of the year and decreases. And so one of the questions is this: why? What's happening to cause the carbon dioxide to increase during some time of the year and decrease in the other? And that answer has to do with plants. So you might recall from a video that the northern forests kind of control the carbon dioxide levels of the planet. Well, why is that? Well, first of all, the northern hemisphere has more land. Since it has more land, it has then more trees. And trees have green leaves, and they undergo a process called photosynthesis. If you don't know what photosynthesis is, it's a good process to remember. Photosynthesis is a way that plants use the sun's energy to create their own energy in the leaves. They take in energy from the sun, but they also take in carbon dioxide. So plants absorb carbon dioxide when they have leaves on their branches. And so what's happening is, in the spring, in the northern hemisphere, trees sprout leaves and they start taking in carbon dioxide. So we're starting at the top of a peak there. And then as the plant continues to grow leaves and take out carbon dioxide, we see the level of carbon dioxide decrease. So spring and summer, the level of carbon dioxide in the atmosphere goes down. Then what happens in the fall? Well, in the fall, the leaves fall off of the trees and they fall onto the ground. And so they stop absorbing carbon dioxide. But in addition to that, they start giving off carbon dioxide as the trees decay. As they break down and decay, they give off carbon dioxide. And if you didn't know this, trees also respire. Respiration is the process of, like you do, when you breathe in, you take in oxygen. Your cells use that oxygen for energy, and you give off carbon dioxide as a waste product. Well, plants do the same thing. They've made the energy with photosynthesis, but they burn the energy in their cells through respiration. So they actually take in oxygen and give off carbon dioxide. And so in the winter and fall and winter, they're no longer taking carbon dioxide out of the air. Their leaves are down, but they're still giving it off. So in the fall and winter, the plants now give off carbon dioxide and their leaves decay, and that adds carbon dioxide to the atmosphere, causing an increase. So every spring and summer, the carbon dioxide level decreases, and every fall and winter, it increases. And it keeps going like that, up and down. But the overall trend, you can see, is an upward trend. So even though we have that up and down motion, the amount of carbon dioxide in the atmosphere as measured at Mauna Loa Observatory is increasing over time. That brings us to the last page. Okay, the last page, we now can take a look again at the Vostok ice cores. Okay, Vostok Station, it's a Russian research station in Antarctica, and these are where you saw on the Bill Nye video that scientists take ice cores and can measure the amount of carbon dioxide in the air. And what we see is, starting on the far right side, that's 420,000 years ago. We can see what the level decreased. So we have what's called an ice age. And then the peaks are interglacial periods, between glacial periods. All right, so we had warming period, cold, warm, cold, warm, cold, warm. And then what should we be doing now? So this one just asks you to be able to read the graph correctly. So let's just take a quick look at question 22. The highest concentration of carbon dioxide. On the graph, you should look to where the line is the highest peak, and that should be right here. To find out when that was, follow that down, and it's between 300,000, 350,000 years. What was the carbon dioxide level 355,000 years ago? 355,000 years ago, I think they're looking at this low point. Follow that over to where it intersects with the y-axis, and you have a value of carbon dioxide, ppm is parts per million, somewhere between 175 and 200. Okay. And there's some relationship questions there as well. All right, so that is activity 3. I would encourage you to go on the activity and take a look at the questions, making sure that you understand the information from that activity. If you don't have any questions, then you're good to go. If you do have questions, make sure you ask your teacher.